So once again, this seminar is being hosted by the Gallagher College of Education graduate student community, where today we'll be having a seminar series from Patrick Pease, our speaker. But before I give an overview about him, I just want to take us through the leadership team of the GSC, where we have Roshan and Rachel as our co-chairs, and the other members of the team, both in the support unit, and then we have our amiable Professor Farouk Mistry as our mentor. And we usually meet, aside from the seminar series that we have on Wednesdays and Thursdays that are open to all graduate students, we meet on Wednesdays at 5 p.m. over Zoom to have a 30 minutes, 45 minutes leadership meeting. Though the meeting is open to all, so if you are a graduate student and you love to get involved in the leadership, you can always join, feel free to join. You can contact Rachel or Roshan through their email to get details, and then we could have a nice time of discussion together. Then we also have an engage page where you can join and then be part of what is going on in the graduate student community. Again, the purpose of the graduate student community is to improve the welfare of graduate students here at OU. So you can bring your inputs, you can bring your ideas, we can interact on the Engage platform and get engaged with what is going on. And then there is also the Facebook page, which also serves the same purpose as the Engage, just another social media platform. Then we have the YouTube channel where we have the seminars like the one that we'll be having today from Patrick being uploaded so that if you miss the meeting, you could always get back and then follow the recordings to get the information. There are other things that we also have in the YouTube channel that I feel will also be useful to a graduate student. Then we also have this resource for team meetings and then study. Like if you want to have a private study, you could have a nice place to sit out with a cup of coffee. We have a refrigerator, and you can see a coffee maker somewhere there on the table, and just the serenity of the environment, just to make sure you get everything going into your mind. Yeah, then please do fill the Google form for the attendance for this seminar so that we could have your details captured. So with that, we will jump into the presentation, give a brief overview of our speaker for today, Patrick Pease, who will be talking about application of early stage modeling to building design, application of early stage modeling to building design. Yeah. And I think one of the things that was quite interesting in my interaction with him in Las Vegas was the COPE tool that he mentioned to me that he came up with and they use in their company to do the design and the modeling. So we'll be talking more about that to us. He is also a graduate student, by the way. He already has a master's degree. So I trust that it will be a wonderful interaction. And I want to crave our indulgence to please be attentive and stay tuned as he gives his presentation. So with that, I invite Patrick to take the stage. Thank you.
Perfect. Thanks for the introductions. I can share my screen and kind of dive in. And I'll go through just a quick agenda of what I'm hoping to cover and then some introductions to myself as well. There we go. So yeah, really what I've kind of put together today is two studies that I've done kind of in my past life when I was working in industry. One was a study where we really looked at the accuracy of early stage modeling. Is this even an approach that would be helpful? And another one where we really simplified that approach to be an Excel based. So trying to, at the earliest possible stage, start to optimize and look at our building energy. And then I want to talk about, of course, kind of what I'm doing today, where I work at Cove Tool, and we have this online platform that's just really focused on enabling engineers and architects to do this type of modeling effectively, and very importantly in the industry, cost effectively, reducing the time it takes to do that, so more and more projects get this kind of really powerful analysis done on them. And then after, I'm sure we're going to have some time for some great discussion as well. So just quick overview of myself. I went to school at Boston University. So up in Boston, I did a bachelor's degree actually in manufacturing engineering. Then I did a master's degree in mechanical. After that, I worked at Arup, which is a consulting engineering firm, where I did a lot of building design in and around Boston, and then also did quite a bit of time in Dublin, Ireland, working on some projects there. After that, I kind of joined with Cove Tool, kind of switching over to the software side of things, where really my focus is kind of using my experience in the industry to build the tools to make all those processes easier. Some things that I'm very interested in, very focused on from my career and now into software is BIM. So for those of you that aren't familiar, BIM, it stands for Building Information Modeling. And it's essentially the modern approach to building design. This is how engineers and architects document the design that will then be built in the real world. So that's something I've become very familiar with through my work, and then seeing how that can be done even better, even more quickly, so that we can build the buildings required by owners and specifications, and still have time to optimize and save energy on that side of things. I do as well do a lot of energy modeling. Now I create the tools to do the energy modeling. I used to just do the energy modeling itself. And essentially an energy model for a building is we'll call it an approximation of that building to see how much energy it will use every day, every hour, and then see it annually. And really what that's used for most often is identifying what strategies you can use to reduce the energy used. Because if we can reduce the energy used, we reduce operational costs. And for owners, that's very important. How much is it going to cost me to run this building once it's built? If I can reduce that from the get-go, that's very important. So what I'm going to go through, I've kind of condensed two previous research studies that I mentioned. The first one is one that I did with some colleagues at Arup, and we presented at the Building Simulation Conference in Rome back in 2019. And it's essentially a look at the accuracy of these early stage models. So the reason we want to do an early stage model is the more decisions we make early in the design process, so nothing's been built yet, perhaps nothing's really even been modeled in those BIM models, time's really written into it. If we can make the right decisions early, the whole project goes more smoothly. So to kind of answer the question of, well, how accurate are these, we did a quick study within my firm where we essentially took a series of final energy models. And by this, what we mean, it's a model based on the final design for the project. So a lot of details been built in, hundreds of hours have gone into these models. They're very, at that point, accurate. And the question really being, if we compare that to the amount of work we would put in say 10 hours or so to create a model, can we get to a close level of accuracy? Is it still helpful to have a model at that stage? And kind of the goal here was really to fill the gap. There's a lot of research out there about simulated versus measured. So measured would be how the building actually operated versus what we simulated in the energy model. There's a lot of good studies out there that look at that, but not so many that looked at that early stage model versus that final stage model. So we're trying to fill that gap with the study. So really, there's a couple of notes here about why the early stage modeling is important. it's all about communications for the engineers and the architects. In industry, you have a design team that is going forward, has really good ideas, knows exactly what the building needs to be to meet, project goals. But if we can't communicate that clearly to the clients, to the building owners, to developers, they often don't get implemented because they'll be confused for things that just cost money and don't give them anything that they need. So being able to communicate, what these values bring, what design decisions can bring to clients is very important. And so being able to understand the accuracy of those was very important. And that's really what the focus of this study was. Can we provide confidence to clients based on the limited amount of work that we might be able to get done at an early stage? So that's what we were going through here. So the methodology for this study was slightly backwards to what we might do in several other studies. In our case, we actually started with the final design projects. Within Europe, it's a very large company, so we just collected a bunch of projects people had already done. And what we're going to do is simplify those back to kind of get a good representation of what that model would have looked like if we had done it at early stage. Put 10 hours of work into it as opposed to hundreds. And then was simply going to study what's the differences of those, performance-wise. EUI is a helpful metric. It stands for energy use intensity. And essentially, it's the annual energy used per area. So it's a way to look at the energy used and compare for buildings that are different sizes, because we're going to normalize by the area. So for the study, we were able to collect several example projects with pretty good diversity. So we had some offices, we had some assembly buildings, some laboratories, all in different climates as well. And essentially these were final models. They were used to show the energy use for, the construction level project. And then we simplified them back. So the way we did that, we were very methodical essentially in, okay, we have a final model, but what would we have done at the earliest possible stage? And we simplified back. So that had a lot to do with geometry. So typically for geometry at early stages, you're looking at things like just window to wall percentages. You're not adding each individual window. That's a huge amount of work, huge amount of detail. So we simplify that back. Also, the rooms within a building, it's a lot of time and effort in these models to capture every single room in a building. So for these early stage models, typically we simplify to simple zoning. So we would have, the interior zone and some perimeter zones only. We wouldn't have every single zone. Similarly, for things like the internal gains, we simplify those back. The internal gains being things like the lighting power density, how many lights are in the building, the equipment, the number of people. Again, a simplified approach would be used earlier on because we don't know as much about the project. We don't know every single piece of equipment that went into that project just yet. So simplifying all those things down. So this is a quick look of kind of what that looked like. So on the left, that would be your simplified model, your early stage type model. As you can see, a lot less resolution as far as details in the windows and also in those rooms. You can see here on the right model, there's all the details. This is an office. There's probably copy rooms and private offices and phone booths. Where in this model, it's just one big open area. And that's a good representation of the amount of effort and time that we can put into an early stage model versus what would be there for the final. And so the question we're trying to answer is the energy estimate we get from this model, is it comparable? Is it useful compared to this one? So when we did that, we kind of ran through, got the simulations all run, got our total energy results. And these were essentially the high level results as far as deviation. So we're looking at, what's the difference between that final model and the early stage proposed. So pretty large range that we came up with, highest almost 50% deviation, smallest maybe about 10%, but on average about 30% deviation. And now this at first can seem like a very large number. And certainly 30% on, out of 100 points would be a lot. But really what as long as we know what the value is, we gain the information to be able to provide to the client what is the accuracy, and then they can plan for that. Because again, with the models, we're trying to make decisions. We're not trying to estimate exact energy use, but we're trying to make design decisions. So if I can say with confidence that, my strategy saves 10% energy in my early stage model, if I know that my early stage model on average is actually showing 30% less energy, that strategy that saved 10% in early stage probably actually saving me a bit more energy, because on total the whole building's going to use a bit more energy. So we gain some data points that we can start to talk very intelligently with the clients about. Just a bit more of that deviation. The average for the full set was about 18, some deviation as well. We did have a few outliers which we cleaned up, which pulled that down closer. But really, from a data analytics standpoint, that 30% stayed pretty much as the answer to what we're looking at for deviation. So if we think about the early stage model based on the study we performed, 30% less energy compared to a final model. We also looked at that by end use. And so end use would be the actual type of energy used, or the piece of equipment where that energy is used within the project. So for a building, this is things like the lighting, pumps, which are pumping around typically hot water or chilled water throughout the building. We have elevators, we have plug loads, all of these types of things. And so we saw some very high deviations for some pieces of equipment, like elevators was very high, exterior lighting as well. And what we actually found for those two items there was that the base assumptions within standards were relatively low. And what in fact we found is people were installing more exterior lighting than the standard might have suggested. So that was one finding. But we definitely saw the largest end use as far as total energy pretty close to that 30% as well. So space cooling and space heating are two large end uses within a building. 30%, 25%, pretty close to the 30% we saw. And then very kind of promising actually is the plug loads, very, very close. So plug loads is the amount of equipment within the building. So this showed that actually those early stage estimates were really close to what was actually kind of happening in the final design. So it was an interesting outcome as well. Just a few data points, which I'll skip through just to go to the next one as well. But you can kind of see where the range was very large. For example, with exterior lighting, one of the projects, the difference was 100%. It was a huge difference. So some definite outliers that occurred. And this gets down to the complexity of projects. Designs change throughout time, so definitely can impact some of these percent differences. And so really digging back to how we use this data to help clients, it's all about talking about comparisons. So if we have a lower EY in that early stage model, we know that in theory, that final stage model will always have more energy use. This means if I'm saving a good amount of energy, I might be saving even more energy in that final stage, even more cost as well if we equate that to cost. And it's an important kind of outlier for clients to show this, because a lot of strategies for projects get shut down based on payback. So payback would be simply put, the energy saved every year. Maybe I save $1,000 every year in energy cost against how much that strategy costs to put in. So if that item cost $10,000 put in, saves me $1,000 per year, my payback is 10 years. Now, depending on the client, that might be okay. a lot of clients, especially commercial type clients, are looking for much shorter paybacks. They want to see their investment return, money back to them within 2 years, within 3 years, maybe 5 years if we're lucky. So being able to present that case accurately really helps keep, energy saving strategies on the project instead of them being removed. So this is just an example of, if we estimate with our early stage project that some strategy has, about a 6-year payback, if I apply that 30% extra energy and therefore extra energy savings, because the whole thing will move up, we might actually have a shorter payback. So that's something we can kind of show to kind of encourage users to, or rather to encourage owners to still consider these ECMs, these strategies to save energy. So that was one study that me and the team performed a while back, and we actually used some of these results on real projects to kind of guide them into thinking about the results they were provided with at early stage, and actually understanding them a bit more to keep strategies, keep ECMs on the project. The next one I want to share is kind of a really unique approach to early stage modeling that I worked on with actually an architect at Perkins and Will. We presented at the I2SL conference. I think it was also in 2019 that we presented this one. And really the focus of this study was to ask, well, how can we get specifically laboratory buildings to net zero? Laboratory buildings have a huge amount of energy use, down to things like the ventilation that's required to keep the occupants safe, and also just the equipment that's running the experiments. A lot of energy is being used. So kind of simply put, what the study was looking at is, the baseline energy or carbon. What could that be? And then subtract from that, potential for renewable. And that would lead us to what the requirement would be for energy. So for this particular study, we started with the assumption that predicted EUI of about 25 or 30 is what's required in order for us to offset that energy on site. And that's a very low number, especially for lab. 25 to 30 EUI is very low energy use. Typical labs are closer to 150 or even 200. So kind of getting down to this was very difficult. And when we wanted to kind of get into this direction, we wanted to do it at the earliest possible stage. And this is an extreme example where by early stage, we mean before geometry is even available. This would be, from a client, perhaps a university saying, I want to design a new laboratory. It's going to be 100,000 square foot, and that's all we know. What can we plan ahead of time to make sure we're getting down to the right location? This is just an example of the challenge ahead for those types of buildings. This is actually from I2SL, which is a sustainability focused organization for laboratory design and operation. And it's essentially the benchmark for laboratories for their EUI. You can see most projects are in this range, 300 to 600. Only a few, actually it was 2, were in the range of 500 or 50 to 100. So very, very low numbers. So the challenge is really immense when it comes to laboratory projects. So what I did, what we did for this particular study was really start to discuss at the planning stage, how can we use energy? How can we use early stage energy modeling to plan the building better? And in this case, what we're planning is the program. So how much square foot of office space should there be? How much square foot of core lab or chem lab could there be and still maintain these targets? So to do that, we created essentially a pre-construction model that we use to calculate the simulated energy use per zone type. And so what that means is we went through when we talked about, okay, we have an office, how much energy per square foot does an office use? We have a chem lab, how much energy per square foot does the chem lab use? And so we were going to calculate all of those out and then back calculate based on a program what the zoned results would be. So really trying to minimize, again, the effort required, because we don't have time at these stages to run a simulation for every single option. That's time prohibitive on any kind of simulation platform. So how can we simplify it even further? So what we did is we kind of ran that initial model and extracted the values kind of in a unique way so that we would have just the zone level energy results. And so you can see where that started with here. So again, we're using EUI. It's a very kind of helpful metric for buildings, where essentially we're looking at the energy use per square foot per year. But this time, instead of reporting for the whole building, each zone type's included. So I can see for an office, my UI is about 38. For a corridor, it's 14. But then, of course, for laboratories, much, much higher. Support laboratories up around 300. Oops. And then vivarium, double that again. So a huge amount of energy is required for these kind of spaces. We also considered that in cost and then also carbon intensity, so operational carbon. What we then did with this is looked at different ECMs. So ECMs is an energy cost conservation measure. It's essentially a strategy to reduce that energy further. So again, we're trying to pick out, okay, how can I drive the energy out of this project? Because energy equals two things. To most owners, it's costs. That's what they're going to care about most. Increasingly, though, it's also about carbon. More and more owners are starting to worry about the operational carbon, which is great. We definitely want to help reduce that. So we're going to look at both those metrics. And so what we came up with was a baseline, so business as usual, and then a series of options that we could consider to reduce the energy even further, because we're trying to get to zero. That's always the goal. Can we get the energy use to zero for that building? We did that for several climate zones, and climate zones make this very interesting for a couple of reasons. First of all, weather is going to impact your energy use. But also, when you look at the carbon determination, the grid cleanliness also really impacts your carbon use. So if you're using carbon as the metric, where locations where there is a clean grid, you can see very different story than if it's a slightly dirtier grid. So for example, in Boston, relatively clean grid, the carbon intensity, for example, for this kitchen, even though it's a cold climate, was lower than in Denver significantly because of the cleanliness of the grid. So there's interaction between grid cleanliness and the weather. So that was kind of an important aspect to include, because it matters not only for weather where you create your lab, but how clean the grid is. So even at that early planning stage is asking, should we be building this lab in this area? Could we build it in a location that has a cleaner grid? Because that would significantly reduce the carbon impact of it. So what we did for this study is we have an example program that we want to try and accomplish. So the idea again, say a university is building a new lab, they want to increase their research capacity. They have an initial program of, this is what we think we want to build. And what we can do is we can essentially plug that in now and say, okay, plug that into the predicted energy use based on the zones. Can assign all that through. And I can see right off the bat, based on the proposed program, I get an EUI of about 276. And so again, we've kind of taken the energy simulation out of the step, so we can do this much quickly. We didn't have to run a simulation for this. We're using predetermined or pre-calculated values and just throwing the program at it to see what comes out. This allows us to iterate very quickly. So instantly we can say to the client, absolutely, we can build a building like that. An estimate for the energy use is about 270. If your goal is closer to 50, we have a long ways to go. And one of the first things we can do is start to play around with that program. So this is an example of where we started to move around the program. Maybe less of the area needs to be actual chem space, maybe much more of it's write-up space, etc., or perhaps more classroom space. What can we move around? So it's really going back to the clients and asking, do you need that much actual lab space that has high energy intensity? Can the write-up portion be split out so the air changes and the energy use can be lowered? And the idea is to kind of show them very quickly. Here's program 1 where we tried to reduce it quite a bit. It got down to 130. And then to get down to 75, we had to do something drastic. We had to take the vivarium out of the program. And so it's really just showing at that high level of if you have a project goal that is to achieve a certain energy target at the program level of the project, you can start to do that. So that's where we kind of pulled it out. And this is a cool example just because I think it shows that early stage modeling doesn't have to even require a simulation platform. It can just occur within Excel. You can get very powerful data out, again, to communicate with clients about what the project's going to be. So next, I want to run through the Cove Tool platform. So those are things I kind of worked on before I joined kind of this software company, where we're trying to do a lot of that stuff that I just talked about, talk about the accuracy of those projects, talk about, how we can impact programming, all of those kind of things, and bring it into this really powerful online platform. So a couple of things about the platform, and then I'm going to dive into, actually, I'll just pull it up so we can see it, is it fundamentally doesn't do anything that other tools doesn't do. There's a lot of tools out there that does a lot of great analysis. This is just an example of it, but really the focus of the platform is scalability. How can we scale these amazing workflows out there so more projects can get this done? Because really, if we're trying to, drive carbon out of the built environment, every building needs a simulation, not just the star projects in an office. So that's a big focus of what the program's doing. So this is an example of, and these are actually several open source tools that do a lot of the type of analysis that we'll see on the platform as well. And again, kind of the key thing of the platform is we're focused specifically on the challenges of the architects. So it's all about time. It's about communication. How can I use the results quickly? How can I make decisions more effectively? And how can I gain support from the clients? How can I make these owners understand that these design strategies are what we need to do in order to deliver them a green building and save energy? The key with an early stage model is we want to do it quickly, and we want that decision to stick. Decisions being like, we should increase the roof performance, have more insulation. If we have that stick, we're actually able to deliver a better project. Things go on into the construction phase, and really we're able to deliver on the promises of the project. So kind of the last slide before I'm going to pull in there. But as I mentioned, again, we're not trying to do anything fundamentally different. The wheel is out there. We're not trying to reinvent it. What we're trying to do is identify the pain points so it can be actionable, so more owners can do this, more architects can do this. So it interacts with all these tools so that when we go to deliver these early stage models, these early stage results, again, we have immediately impact on those projects. That's really the focus of the online platform. And that's really the evolution, I would say, from some of that early work where we did a lot of work. It was time consuming to do a study where we looked at your early stage and then final models. It was time consuming to make that data set for that Excel file. But now what we're trying to do is take that time-consuming task, make it very finite so that we can do it on every single project, really spreading that and democratizing it. So let me pull up the tool. I think I have about 10 minutes left, 20 minutes maybe. Looks good. And I can talk through kind of what the platform is, what it does, and then how essentially design teams can use it and do use it, on their day-to-day projects. As I've already mentioned, it is an online platform. So everything that happens, all the simulations, access into all the projects, happens here, in the browser. I have just an example project I'll run through to show kind of what's going on here. For each project, we start here. This is our project setup. And essentially what we do is we just capture some info about the project. What is the project? So we can automate in as much as we can about it. One way to get not only speed, but repeatability. And repeatability, we're talking, did I use the same inputs on this project I did at the beginning of the year to the one I did at the end of the year, or did I make a mistake? By doing, assigning those inputs automatically, I have some confidence that they're going to be correct each time they're put in. So really right here, all we're going to ask or put in, what's our building type? Buildings come in all shapes and sizes. But really what we're asking is, what's the main program? What's happening in this building? So, is it an education? Is it a university building? I've selected, I'm doing a hospital here. Is it an office, etc. So we're going to assign that first. Next, we're going to do a location, because location is very important to projects' energy use. Projects, depending on the weather and also the adjacent buildings, energy use will be different. So having the exact location makes it very powerful. So we're going to add in that location. The other important thing for every building is the energy code. Buildings are built to code. These are standards put forth by either typically states or local governments that have usually minimum performance requirements for the project. So we're going to essentially, we've documented those and we'll automatically assign those, because at the very least, projects have to meet those. We always want projects to go further, and that's why we're encouraging them to do energy models. But as the starting point, that's what we're going to work with. The next thing we're going to need or want to do is talk through geometry. Now, we looked at a couple different means of geometry in those slides. So we have, early stage geometry, where it's essentially a massing model. We have different zones. We have that final stage, super detailed geometry. We looked at that one as well. Or then even just the simplified, per square foot geometry. So that Excel example was probably the most simple form of geometry you can do. So what we've done with the platform is actually enabled us to look at all of those as well individually. So the idea being, no matter what stage of a project I'm in, no matter the information I have about the project, I'm able to work with it, on the platform. Let's open that new tab while it's loading. So one of the options being manual mode, and manual mode, that's the Excel that we looked at. It's literally just numeric values. And again, at the earliest stage for a project, maybe I can enter these in and I can run with it. I can get some data out, which is fantastic. Everything after that will be 3D. Buildings are, of course, 3D by nature. So we'll look at those models in 3D. Let me run through really quickly what this example model looks like. This is just an example massing model for a hospital. So I have it created here. And really, again, the idea is it's very simple. We have, windows that are assigned just by the window to wall ratio. I have all the walls defined, the roofs. These are the fundamental building blocks of my model, my analysis model. Once I have this created, this geometry, I can then start to do some analysis on it. Oh, my page didn't load. We'll stick to energy when that loads. And what that's going to look like is something that's meant to be actionable. Again, the goal of this platform is for architects and engineers to get the information quickly, make decisions, and then move on to the next step. Because really a barrier with early stage models is, even putting them together can take, tens of hours, multiple days. So we want to be able to do that within minutes. And so in this project, the steps I've taken, I said what it is, I said the type, I drew my geometry here because it's nice and simple. I'm just exploring what this might look like. And then I'm going to run the simulation. Now the platform runs on an engine which is called the ISO standard engine, and it's based on some European standards for energy estimation. So it runs very, very quickly. And by quickly, I mean literally in a couple of seconds. And it also importantly uses what we term a reduced ordered inputs. So certain things I'm able to modify, certain things are going to be held constant in all the simulations. So the performance of the project, I can define, the uses and schedules. We looked at these in the example in the Excel, different labs have different internal gains. Those are all things we can start to capture here. Different building systems as well. Those are the HVAC systems. So really what we're doing is we're capturing all that information, putting it into a simulation, and then producing these metrics. And really the idea is these metrics let us make decisions. So first of all, back at EUI, that very important metric that we're always comparing, what is the UI based on these decisions I have inputted? What's the operational cost as well? And then looking at what the carbon is, this would be the operational carbon. So again, how do we display that for every project so it's understandable and it's in a format that compares itself to a benchmark? So this is really powerful for, again, architects and engineers to share with their owners, to say, if we go with these design decisions, yes, we can reduce your operational carbon X amount. Yes, we can be so much above, a benchmark, all of that, important information. Finally, like we saw with the end uses in that first study, we're going to show all of those. So we can estimate as well, my heating load, is high, equipment is also high. These are the two highest ones. And I can know if I need to reduce the energy use of my project, that's what I need to focus on. Also, based on the accuracy of it, I could estimate that this might be even 30% higher. That means I really need to focus on it because it's driving the energy use of my project. It's all about making these things evident for the engineers, for the design teams, for the architects, so we can action them and make differences. The next piece I want to show is actually where the platform started. This is the cost versus energy optimization. And this is really, where we're trying to get on every project. So we talked a lot about, what clients need to see, how do we communicate them? We always got to talk about costs. People that build buildings, whether they're developers or universities or, local governments, have budgets, they have goals related to money. So what this tool does is takes that model, takes the cost of equipment, cost of the building itself, looks at the energy savings we might be able to produce, and then let's just look at things like the payback. So here, essentially, I look at a series of options. Those options get bundled together, and then each bundle I'm able to explore. So here I'm going to select for just a few of the payback options that are at the lower end of the scale, but also the highest energy savings, because that's what I care about. And it gives me these suggestions. So now I can bring these to my design team and say, if we go with this option from the wall, this option for my HVAC system, I can arrive at this great outcome, which is 25% energy savings at a payback that's maybe 14 years. And I can use that as the starting point for a discussion to refine it even further, and again, drive the energy out of these projects. So this one in particular is very impactful, for the design teams when they're talking with the clients, because we want to show, not only is our designed good, but we thought of all these options. We've looked at opportunities to save you, the owner, operating costs, operating money, and we have a suggestion how we should move the project forward. This is really impactful because it does let us arrive at better outcomes for the projects, and that's really the goal of the online platform. One of the other things I did skip over because it was loading. No, it's still loading. Here it is actually some of the daylight analysis as well. So another kind of early stage type analysis that particularly architects really need for their project is the daylight analysis. Especially office buildings and educational type buildings. Daylight's a very powerful resource. We experience a room, a space better if there's some daylight, if there's some view to the outside in it. And it's much more pleasant to be inside. So one of the things architects think of a lot early stage will in fact be that early stage analysis, or sorry, the daylight analysis. So the platform provides that as well. Again, trying to tie in all aspects of what they need to know about a project in a fashion that's very easy to access and run with. And I think it's just slow to load because I have Zoom going at the same time, but that should load in a second. How am I doing on time, Andrew? Do I still have a few minutes?
Yeah, I think you still have a few minutes.
Okay, perfect. Yeah, so this is going to load quickly. But yeah, just to speak to some details of what's happening here. This analysis that's about to load is our daylight analysis. So again, how much quality daylight is that space getting? And that depends on where it's located, not only in the globe, but this is actually downtown Boston. So there's a lot of buildings nearby that block daylight. So being able to account for those early, again, making design decisions based on those is very impactful for the projects. If I want to increase the daylight in my building, I can see instantly where I'm at. Again, as I mentioned before, I am an engineer, so I didn't do that good of a job that an architect would have done getting good daylight deep into my floor plate. But I can see that right away and can start to make changes. And that's really what early stage modeling, whether it's for energy, whether it's for carbon, whether it's for cost or daylight, is all about. How can we understand what's happening quickly so we can make a change? That's the goal. We want to improve, but we need to know where we're at before we can improve. Change for change's sake isn't design. We want to measure how that initial design is performing and then make improvements upon it. Being able to do that quickly and multiple times is really where the early stage modeling comes into play. And here you can kind of see, not only what that looks like, but you can see we're getting metrics loaded as well for each floor plate, as they load in from the back end. So a lot of detailed information that architects can receive very, very quickly. The other thing I wanted to share, just kind of as we're on the webpage, is that we do offer educational licenses for the platform. So if any of you are ever interested in jumping onto the tool just to check it out, I'll definitely share this link. It gives you essentially log in with your edu email, which of course you have, and then you can have full access to the entire platform. So we really encourage anyone in academia that has interest to definitely check it out. We've even been reaching out to some K through 12 schools as well in the local Atlanta area, which has been really exciting. Getting some middle school students and high school students excited about building design and energy has been really, really rewarding. So definitely worth checking out if you're at all interested. I think I can pause there and kind of capture any questions that might have come up. I know we kind of went through quite a few topics there in a short amount of time. So really interested to see if there are any questions or thoughts that we might be able to discuss further.
Yeah. Thank you very much, Gina Patrick,
Yeah.
for the nice presentation. I think I'm excited to see, like as a graduate student, to see that just like us, the research you did during your studies, you've been able to translate them into practical solutions that you're using out there in the industry to bring help to people, help them, like reduce their energy consumption and society at large are trying to bring carbon reduction, which is kind of big deal right now with the climate change and all of that. And then also seeing I think another part that was quite interesting is the scalability part that you talked about in the tool, because that was kind of the first question I had. Could this be, adapted to maybe like a residential system, which I mainly work with? And then I think you covered it from the slides. I could see that the tool is quite a very elaborate one that covers the different building types. Yeah, so one of the questions that came from the chat from one of the participants who had to leave for another meeting, um, which kind of links with what I had in mind. I know you talked about the focus not really much on accuracy, but more of the, impacts. But I was curious to know if there is any kind of evaluation or benchmarking or, calibration
Oh.
that you've done on the tool that you talked about, the Cove tool. And so one of my colleagues was asking, what's the difference between the Cove tool and the Revit BIM software? I was also thinking of the few I know. Like you mentioned, there are a lot of energy modeling tools out there. They even do optimization with those tools. So maybe we should start from there. Then we take other questions as they roll in.
Yeah. No, that sounds excellent. All right, let me stop sharing my screen for a second. So starting with the first part of that question of how do we, I guess, validate these platforms, these energy simulations.
Yep.
So there's a standard produced by ASHRAE for a test procedure. So it's ASHRAE standard 140, and it's essentially a test procedure that has, off the top of my head, I think it's almost 80 or 100 test cases where it's very explicit of, a room of X dimensions with a window of this performance at this location with this weather file, run the simulation, do the results match these, established values. So that's a standard test case that we use. We test the software against that. And it's very helpful to have, that standard out there in the industry, because yeah, absolutely, your question is there's so many different tools, how do they compare? This gives us that like standardized approach to compare them all. So that's one that we use specifically for the energy result, actually. So ASHRAE standard 140. There's
Okay.
other standards as well. Um, Also from ASHRAE, this one ASHRAE standard 183, which is doing a very similar thing. It essentially has, some requirements around, how the simulation is set up, how it's handling time steps, things like that. And that's,
Mhm.
again, just an explicit, almost like a checkbox kind of thing. It's like, do you do this? Yes. Do I do this? Yes. And so that standard is also very helpful to be able to reference as a way to confirm that, yes, the simulation is being done correctly, for the industry.
Mm. All right. Yeah. All right. Thank you for that. I have a lot of, or like a couple of other questions, but I think I would open the floor to get questions from other participants. If anyone else has like a question, Swapnil, do you want to jump in? Maybe with your question, while others could come up with theirs as well.
Yeah, I just had one quick question. So, so the software which you showed, is it available only as a commercial thing, or like is it available as a let's say a student version kind of a thing where the
Yeah.
college students can do some projects so that
Mm.
like it can so like how answers and these softwares have analysis things for students. So is that available in this software as well?
Yeah,
Yeah,
definitely.
it spoke my mind. That was another question I had. So go right ahead.
Yeah, so it is absolutely available for students. I'll share the link in the Zoom, essentially how to sign up for it. So it is an online platform. Essentially, you can sign up for a student access account, and it's full access to the platform. Kind of everything you saw, you absolutely have access to. So I'll share that.
All right. All right. Thank you.
I
Thank you
just
very much.
so I just had a quick follow up. So is the student version like free or is it like a charge or can the university get a license from the
Oh
company
yeah,
itself?
it's absolutely free for educational use. So no issues
Okay.
there at all. Yeah.
Plus, it's full access from what he said. So there's no limitation, right? So, oh, wow, that's interesting. I
Yeah.
think would also love to share that with other graduate students because
Yeah.
we have a lot of students doing energy design, modeling stuff. I mean, I took a course last year and we kind of touched on all of the things I saw in your slides, SHGC, the building envelopes,
Oh
and
yeah.
then the shading and all that. So they kind of used Excel, which is more like just a manual way. But I think one of the things that was very interesting in your talk was your thinking process about doing something that is smart, like automated, which is really what I usually love. Like when we have solutions, we should be able to make it replicable so that each time we have a problem, we don't have to go through the rigors of formulating and all that again. Yeah.
Yeah, definitely. Repeatability is a big focus of the team, as we develop the tool. So he's thinking about, okay, we meet thousands of, if not tens of thousands of buildings per year. How can we make each one even easier to do? And how does one, grow on the next one? Yeah, so repeatability is a big thing. And in some parts, it's one of our main focuses. A lot of the analysis, as I mentioned, that we do, a lot of it's becoming standard. We simulate for energy, we look at the energy use, we simulate, we compare that to carbon as well. These kind of things are becoming standard practice, but doing them in a repeatable fashion, that's really what we're trying to unlock. Because it's all about, again, scaling it. Because we want every building to have an energy model. And there's some, I don't have the exact statistic, but the AIA, and so that's the Architectural Institute of America, does some surveys to find how many projects get an energy model, and the number is in the high teens, so very very low compared to the total buildings built in America. So trying to attack that, we're talking like 80% of buildings don't get an energy model. Trying to get to those buildings so they know how much energy they're going to use and hopefully reduce that energy is huge.
Yeah. Oh, okay. While we maybe get some questions from others, as they prepare their questions,
Yeah.
another thing I wanted to also touch on is, yeah, I think one of the things that I've really been very interested in, um, especially because as graduate students, we always try to think in terms of transition from academics into the industry after graduation. So the core tool, was that like a software you built from the scratch and maybe patented and then so how did you go through like that process, if I would put it that way, of you know getting to build your own software and then getting the patent for it and then using it to the point where you build confidence in the like in the market, in the commercial markets, that yeah, this tool is something. I mean, because from what you shared, the tool looks to be well advanced at this point. Looking at the interface and all the things that you have built into it, I'm like, wow, this is really some very robust tool that you have there. So how did you go through that? Um,
Yeah, definitely. So The starting point for the tool, it's always a lot of planning first before we kind of even start to make, you know, a new function. So I'll take, for example, one of the things that we built out since I joined was a huge series of additional HVAC systems that we could simulate. And so before we even, you know, got into, you know, starting to program those in, et cetera, we did a lot of kind of background research just to know, have confidence, you know, is this the right thing that users need, you know, that engineers are modeling, are these the right, you know, are we asking the right questions, are we finding the right answers? So a lot of kind of like pre-thought goes in first. Then we do, essentially, we call it an R2D2 process, where we research, you know, again, all the steps, are these the requirements that are required, develop, you know, some framework of what we think it wants to look like. And usually what we'll do is someone will do that in isolation, like an interface, someone will do that in isolation. And then we share that back with the wider team, kind of like a pinup review, and say, okay, do we think this makes sense? You know, the way it's organized, all of that, getting feedback and trying to iterate quickly. Because it's never, or rarely ever, will it be your first idea. That's what you want to build kind of all the way through. So iterating on each step of the way is very important. Then we go through the process of developing, and being a software company, we have, you know, full-time software engineers that do the programming, which is fantastic. You know, the quality of code that a trained software engineer can produce is very good. Certainly better than what I can produce kind of as an amateur. And then it's all about the QA process, the quality assurance. You know, testing is very important. So we go through very rigorous testing. We come up with test cases of, okay, we know based on our research, if I put in these inputs, I should get this, you know, output. We run that again and again. In some cases, standards like ASHRAE 140 help us do that because there's some predetermined thing. In some cases, we need to come up with that ourselves. But being able to have that is very important because we want to be able to say to the users, and this is important for building confidence in a tool, that yes, we did this process. Yes, we checked these things. You know, we went through a lot of rigor before we even released it, you know, to be used. So that's a big process as well. As far as time spent, you know, it's almost the same length of time as the actual development, the testing, and the, you know, minor tweaks after that to really refine and improve. So making sure you have those kind of really clear plan early before you even start to program, you know, digging into the use cases, having it reviewed and kind of, you know, pick it apart. You know, can we do this? Can we do that? And then that quality assurance before you even release it to the wider public really helps. And I think that's, you know, a big part of, as a software startup, where we shine, because we're able to do that process relatively quickly because we're able to be agile with all of that. But keeping focus on quality is always, I think, the most important part to any kind of tool like this. Because as we already touched on, I think you kind of touched on it too, Andrew, is, you know, having a tool that works, you know, you've done some research, you have it, it works for you, great. Making sure it works for everyone, that's where the magic happens, and that's where that quality assurance and that kind of user workflows come into play as well.
Yeah. Yeah, thanks for that. Yeah, I know it's expected to be a kind of rigorous process, but it's good to see how you guys were able to have that edge in terms of how you were kind of like at the leading edge in terms of like the simulation, you know, that having the right support. Like, I know it's more like a teamwork as well. You had software experts who also teamed with you to get it done. So yeah, I think the last question I'm going to ask for the sake of time is so the question that most graduate students always want to ask in in meetings like this, because as graduate students, we're also thinking about building our career. having internship opportunities or future job opportunities. So are those available from, your company, from your end, and how, how possible for graduate students to access those opportunities?
Yeah, absolutely. So we are growing pretty consistently and very fast. Currently, we're kind of targeting probably another round of kind of growing the development team. So that would be kind of the research team that I think people on the call would be interested in the spring. And so I'll share a link as well to our career page where all those will be posted. But we absolutely hire, graduates as well. We recently hired last year a graduate from, oh, he's gonna kill me if I get this wrong, University of Cincinnati, I believe. So we absolutely, look for that talent pool to kind of grow the teams. I'd say I'll share the link to the career page. Definitely worth checking. Things will go live probably in the spring, and also feel free to kind of follow me on LinkedIn. We do a lot of our kind of sharing of news via LinkedIn, so I can share my LinkedIn as well. So feel free to follow me. When this goes live, I'll of course be sharing them and stuff. But yeah, no, absolutely.
Okay, yeah, that's great. That's fantastic. Yeah, Avinash, I can see your video turned on. You.
Yeah. Hi. I have just a quick question, Patrick.
Yeah.
So first of all, wonderful presentation, and I really like the tool. I was wondering, as you have the education license, do you have some I don't know, some kind of online course to just for a brief
Oh, really?
introduction to how to get used to the tool and how to explore that?
Yeah, definitely. I can actually share my screen again so I can show that really quickly. But we absolutely have a lot of resources. Hang on, let me find it. I can share my screen just to show those. So we kind of have two main resources available. We have a ginormous help center.
Okay.
So the help center is a series of, essentially it's the manual for the platform. So all of that's freely available. You don't even need to log in to access it. We also have what we lovingly call our Cove Tool Academy. And so this would be that self-paced course. So absolutely one you can take, and those are free to take as well.
Wow.
Okay. Yeah, that's wonderful.
Yeah.
Yeah. Thank you so
Okay.
much, Patrick. Yeah, that's
definitely.
wonderful.
All right. Yeah, thank you. Thank you so much, Patrick, for the wonderful presentation and sharing the resources that you guys have. It's good to also know that you're not just thinking about making the money, but transferring the knowledge you've acquired to graduate students, to other graduate students, to like younger engineers, but the resources you have, put together. I could see even in the slides, or like when you shared your screen, you have some webinars that you also organize to train young engineers on how to use the tool. So that's super wonderful, and I'm excited. I'm glad that you honored our invitation and gave such a wonderful talk. I apologize on behalf of our mentor who had to excuse himself. Yeah, he has an appointment. He usually stays all the way to the end, and is usually the last person that leaves. But I guess it's the time of the semester where all hands have to be on deck because of the midterm exams and then the finals coming up. Yeah, so
No
even the
worries.
graduates, yeah.
Yeah.
Yeah. All right. So once again, on behalf of the graduate student community, on behalf of our mentor, he specifically asked me to send this thank you to you. He's grateful, and we are all grateful to have you with us today and giving us the liberty to record this, which we would upload on our YouTube channel. And then we look forward to getting more communications, more interactions with you in the future. And we wish you well in your future endeavors and pray that the the Cove tool, the industry, your team, you guys could keep getting better at what you do, and yeah, make more impact in the energy industry.
Yeah. Thank you, and thanks
All
for
right.
inviting me to join and share today. It was great to kind of share with everyone on the call.
Yeah, thanks. And thanks everyone for staying back, for those that are still on the line, for coming around. Thank you all. All right, so I think I will end the meeting.